Hello everyone. I'm Ghulam Qadri, assistant professor at University of Oklahoma, and this work was conducted during my appointment as postdoc at University of North Carolina Chapel Hill and was completed in collaboration with Arran Wang, Zhehao Wang, Jennifer Adorno, Paul Rosen, and Danielle Albers Szafir. Let me ask you a question about this graph. What do you see in this graph? You will try understanding the overall knowledge you can build from this graph. Now, if I ask you, estimate the correlation between income and rate of death. You will be specifically looking for correlation between income and death rate, which says lower income correlate with lower likelihood of vaccination, which in turn associated with COVID deaths. The quick use in this task, that is, instructing people to estimate a given statistics, may direct people's attention to statistics or pattern that are otherwise not immediately obvious, and to assess and measure the effectiveness of high-level analytical or communication goal of visualization. Graphical perception studies typically measures people's abilities to estimate individual pre-specified statistical quantities, such as estimate the correlation between income and rate of death. High-level comprehension, in contrast, describe the overall knowledge a viewer intuitively gains about data without explicit cueing or guidance. In this work, we explored the interpretation to examine alignment between designers' communication goal and what their audience sees in a visualization. In other words, do users actually see the information the designer intend to communicate when they are not cued? We'll follow this outline to discuss the progress of this talk, which is methodologies, analysis, results, and takeaway. We designed two tasks to investigate whether graph communicate the information they were designed to communicate and to elicit the specific types of patterns or statistics people notice in different visualization types, which are describe what you see in the graph and what questions would you be able to answer from this graph. Our study investigate visualization that vary in visualization type, data type, and graph composition. We selected and tested three visualizations that commonly used in media: scatterplots, line graph, and bar graphs. We selected datasets to plot graphs with either single class, no categorical data, or multi-class data can be decomposed into categories. Visual tasks often require comparing data across groups or dimension. We considered graph composition through either juxtapose or unjuxtapose designs. To create a stimuli design for study, we drew the inspiration from graph in data journalism. These graphs allowed us to explicitly understand their intended goals by mining targeted statistics from accompanying text and reflect known best practices for communicating this data. Our reproduction used the general schema from the original graphics, but we replaced the data and associated labels and values with the data from 42 stimulus datasets to remove potential interpretive biases associated with data semantics. We try to mirror the design choices from the original graph as faithfully as possible while minimizing potential framing effects when adapting visualization to the target datasets. We recruited in-person participants from a university campus. During their study, experimentally explained the task and directed participants to a web application where they completed the formal trial. We did not include any tutorial examples to avoid potential bias from priming. Participants completed two tasks, target task for a sequence of 12 visualizations. Participants provided their responses to each questions in a text box. We encourage participants to verbalize their reasoning to collect additional insights into strategies, points of confusion, and salient information that was not reported in open-ended response text. We used actual coding to analyze the natural language inputs From both the text responses and transcribed verbal utterances from think-aloud protocol using the codebook derived in our pilot study. We coded each responses for its comprehension match, statistical task, and design and data critics. Comprehension match quantifies the extent to which a participant's response align with the stated objective, as inferred from accompanying text of the source graph and participants' natural language descriptions and verbal responses. This metric helps evaluate whether participants accurately perceived and convey the statistical information or insight that visualization were designed to communicate. We have four categories of comprehension match: complete, general, partial, and no match. For example, a complete match indicates a strong alignment between participants' responses and design objective. In such cases, participants have effectively comprehended the key statistical information and insights intended by original graph. Statistical tasks encode the key pattern and statistics participants provide in the responses. We employed Amar et al.'s low-level task taxonomy to code this task. Data and design critiques identify feedback provided by participants about how a particular design choice or the data itself assisted or hindered their comprehension of visualizations. We did not ask participants to provide a critique directly, but documented critiques that arose naturally in responses or think aloud. While not directly related to our core research questions, these observations provide additional insight into visualization design guidelines. The patterns people reported seeing in visualization failed to match stated intention in 59% of tested visualization. We found that visualization communication goals do not always align with knowledge people draw from a graph, even when following best practices. In order to explore the data, we analyzed participants' responses data using thematic analysis and found three overarching themes in order to understand the need for visual comprehension as a metric. For sake of time, I will be only discussing theme 1, but I'll encourage you to read our paper for more detail. Stated communication goal does not always align with knowledge people drew from graph, and this result echoes calls made in more comprehension-oriented studies to understand better the connection between design guideline in theory and their efficacy in practice. Moreover, the stated design intent may not always align with people's comprehension, as a comprehension is influenced by multiple factors, including visualization design, individual's background, graphical literacy, and supplemental information. An expert crafted visualization intended communication goal may not always align with insights and salient pattern people intuitively extract from that visualization. This is demonstrated by the result, where only 41% of responses completely matched the designer's goal. And 77% of those matches were provided by 10 participants who provided complete or general matches for at least 10 of their 12 stimuli. The strength of this alignment varied by graph complexity, such as visualization with multi-class data or juxtaposed subgraph, which says that the complexity and the graph juxtaposed nature hindered the comprehension in the people. People tended to quickly identify the peaks and valleys and change over time in line graphs, maximum value in bar graphs, and correlation as scatterplots, which means that people can easily report specific statistics for certain chart types. In many cases, people frequently fail to find irrelevant patterns in visualization with multiple categories represented using multiple encodings, where position, size, color encode different data aspects, where tasks grow difficult with increases in complexity. For example, participant 13 said that I could understand bar graph and simple line graph, but not scatterplot or graph involving multiple categories. We observed more than 30% responses failed to identify any alignment in the stated objective for this graph. For visualization with multiple categories represented using multiple coding, participant response significantly deviated from intended communication goal and focused on what they can read on graph. For example, for the given graph, participants 1 basically read the graph saying an increase in how many dollars are earned per week between earnings of production and non-supervisory employees and earnings of all employees. We found a correlation between number of charts and alignments with the stated design intent. Specifically, fewer chart leads to higher alignment. For example, non-juxtaposed chart tended to support higher alignment than other kinds of composite charts. Similarly, several misalignment arose when participants found the graph difficult to interpret. These instances largely occurred in complex visualizations, most notably juxtaposed graph and multi-class data as shown here. Our result offer a set of general consideration for visualization design and researchers helping reconcile prior findings, providing implication for applying design heuristic and lending insights into a methodological consideration for visualization evaluation. We identified these general guidelines under three takeaways. However, I'll be discussing takeaway 3 for the time's sake and encourage you to read our paper for more detail. Conventional design guideline visualization often suggests that a task for a given visualization is effective for, such as a scatter plot for clustering, distribution, characterization, and correlation. However, these guidelines are typically based on experiments where people are explicitly cued to identify specific statistics. Task effectiveness as control settings may not always translate to real world scenarios where people may approach visualization without predefined goal in mind. Our result indicates a need for broader range of methodological consideration generalizing from empirical studies to design guidelines. A statistic focused and directed research task may invoke a cognitive process known as cognitivization of perception. This cognitivization may change how people engage with the visualization, causing them to note different patterns as being more salient than actually are. In practice, this implies that just because people can estimate a statistic from a given graph does not mean that they will estimate that statistics, at least unprompted. Our findings offer a preliminary step towards designing for graph in wild without the risk of cognitivization. We ask participants to identify questions each graph address. This new experimental task in turn led to significantly more statistics tasks and specific patterns emerging in people's responses. Best practice in survey design encourage asking about target topic from different perspectives to avoid framing bias. Our results also indicate a need for general design guideline for better consider the knowledge people naturally extract from visualization. We cannot fully understand how people derive insight from graph exclusively by experiment using cued experiments. This confirmation reinforces the need for a diverse range of methodological paradigm in visualization evaluation. Thank you for listening to my talk.